Our next topic is called mathematical induction. Now, this is a type of proof, and it's quite a formal sort of proof. Now, before we start, let's just think about what the word induction actually means. If you induce something to happen, then you cause it to happen, or you persuade it to happen. So in mathematical induction, we need to persuade the reader of the truth of some sort of statement, and we do that in quite a formal way. So first, we've got a description here. It's a method used to prove that some statement is true. Now, it's for integer values of some variable. So if we have some kind of equation and we want to prove that it's true for all integers, then we go about it by setting out basically three different sections of the proof. And you can name them section A, B, and C, if you like, so that it keeps the structure there and you remember not to leave any of these parts out. Now, the first part is where we show that the statement, whatever it is, and this will be some sort of equation or formula, we need to show that the statement is true for some starting value. Now, I've written here, for example, n equals 1. Now, it might be that the most logical starting value might be n equals 0. It'll depend a little bit on the situation, but for many of them, we'll start with the first positive integer. And remember, I've said here that it's generally integer values that we're looking at, and in fact, it's usually positive ones too. So we start by saying, okay, let's show that this thing is true for a starting point, let's say when n is 1. Then we say, all right, let's suppose that it would be true when n equals k, where k is some integer that is greater than or equal to 1, okay? And we then prove that the statement is going to be true if n is just a little bit bigger than k plus 1. And then we finish off by saying, okay, it follows from parts A and parts B by mathematical induction that the statement is true for all integers greater than or equal to 1. So here's the thing, we're proving that it works for 1. We're proving that it works for some integer k, which could be anything that's bigger than 1. And then we say, is it true for k plus 1? Because if it is, then if k was 1, it would be true for 2. If k was 2, it would be true for 3. If k was 3, it would be true for 4, etc., etc. Therefore, we can say it's true for all positive integers. Now, what is true? Well, I said we're going to be proving some statement. There's certain types of statements that really lend themselves well to mathematical induction. And in this little mini topic, we're just looking at 2. So in the first exercise, we're going to use mathematical induction to prove the formulas for some sums of series. So that's why we're doing this pretty much straight after looking at sequences and series, because it's a recursive idea of looking at how we can add up some things to equal some formula. And then in the second lesson, we're going to prove divisibility of certain statements using mathematical induction. Now, when you're setting out your proof, there's a few things that are really good to write down exactly as is. Have you noticed here that I've put inverted commas here on statement C? You should always finish your proof by mathematical induction with this sentence. So we literally have to almost just learn this like a line from a play and literally write it down exactly like that at the end of every single proof. So that's in inverted commas. Now, what about these other parts? Do they need to be set out exactly like this? Well, yes and no. For the first bit, if we're showing that the statement is true for n equals 1, the best thing to do is just to write let n equal 1 and then sub in 1 for n into your formula. And if it does work, then you can say, therefore, the statement is true when n equals 1. So yes, you need to write something about how it is true and by showing it. You should write this part here. Suppose that the statement is true for n equals k, where k is greater than or equal to 1. That's a good part to write down exactly as is at the start of part B. When it comes to actually proving that the statement is true for n equals k plus 1, I wouldn't start by writing this. I would say let n equal k plus 1, and then you're going to sub that in. And if it is true, you'll say, therefore, the statement is true when n equals k plus 1. So yes, you do need to write this down, but maybe not as the starting point. Now, this will make more sense once we look at an example.